conference. It's my pleasure to introduce our first speaker, Professor.
Thank you. Yeah, I'm happy to be here. Maybe many people have presentation on artificial intelligence here, but also the conference has the name Formal Methods, and my presentation is about to show that if we think a little bit other way than what is the conventional thinking, we may have some tricks, and then we may have much larger expressive power, or we can do much interesting things by traditional or close to traditional way. So the title is Non-Traditional Final State Machines, like automata. So here is the outline. So I will talk about, first just to show what is traditional finite automata, then we will go to multi-head automata, and especially I will talk about Watson-Crick automata, then automata with translucent letters, and then I will mention in the end jumping automata as well. So just to see some historical things, so the traditional finite automata dates back to 1950s, 60s. The classic results of multi-head automata is from the 1970s, but there are recent results which are like defined in the past 10 or 15 years. And so what is a finite automaton? That's a 5-tuple, and it traditionally reads the input from left to right, because we usually express the input as a string. But we will see that we have many parallel and distributed systems, and therefore we may have some non-traditional automata as well. So, as I told, first large topic is multi-head automata and Watson-Crick automata. So a multi-head automata, now we have more parts. K is the number of heads, and we have, so we have two markers for the beginning and the end of the input, because if we have more heads and these heads can go maybe independently but in a correlated manner, then we need to know if one of them reached the end of the input. Therefore we have and if we allow two-way movement of the head, then also we need to know if it find the beginning of the input. And the transition function is defined in such a way that we can never go out of the part of the input with these two sentinels. So basically we have again non-deterministic or deterministic automaton. So here we have that all the K heads are watching either an input letter or one of the end markers, and basically it's the non-deterministic variant. This 0 and 1 means if 0 means the head doesn't step anywhere, it stays at the point, and 1 means it goes one step to the right. In two-way automata, we may allow step to backward as well, but only if the head was not in the first marker. In deterministic variants, of course, we have just a state, and the head movements are exactly one possible continuation of the computation. So here I put an interesting example when, for instance, the input starts with A's, then with B's and C's, and the automaton may check if the number of A's and B's match, or the number of B's and C's, or the number of A's and C's match, and we can do it with two heads which may scan first the A's and the B's together, or the B's and the C's together. And then if the steps are correlated, then we don't need to have so many states for this checking. So there are basic hierarchy results. First, on the number of heads. If we have more heads, we can do more things. So if we have a dragon with 7 heads, it can do more things than a dragon with only 3 heads. And this is going both in the one or the two-way directions as well. Yeah, these are classic results. And another hierarchies between the deterministic and non-deterministic variants. What is interesting, if we have at least 2 heads, then we may have a language that we can do it with non-deterministic automaton with 2 heads, but doesn't matter how many heads we have with deterministic machine, we can't do it. So on the bottom of the hierarchy, when we have only 1 head, then doesn't matter if we allow 1-way or 2-way, we can accept exactly the regular languages. Also, if we have only 1 letter in the alphabet, then again, doesn't matter how many heads we have, we cannot really do more than what we can do with 1 head. So only the regular languages can be accepted when the alphabet is unary. So we may also have so-called sensing variants when we can use the heads as markers, when the automaton not only knows what is under the head or if the head is already in the one of the extremes of the input, but the automaton senses if one of the heads is in the same position as some other head. And in this way, we can do languages which are non-semilinear in poric sense, which means we can break the barrier what was in the previous example stated for the classical variants. Now I'm moving to Watson-Crick automata. These are motivated by the structure of DNA, so like 20-some years old models. So basically, instead of a normal input, we think about the input as like a Watson-Crick tape, when we have some, based on the Watson-Crick complementarity, 2 strands. The original nucleotide alphabet is like adenine, cytosine, guanine, and thymine. So we have these 4-letter alphabet in DNA. And what is interesting that the adenine is also paired to thymine and cytosine to guanine. This is because of the size of the nucleotides and the hydrogen bonds between those. And the strands have opposite 5' 3' directions. So, yeah. So Watson-Crick automata, usually abbreviated as WK automata. And from biological motivation, we may think about that not only letter by letter, but strings may be read in a transition. So this is like a schematic form of the Watson-Crick tape, like a DNA molecule. We can see that adenine and thymine can be pairs and so on. And like we have a finite state machine, and we read both stands. So this is just like a 2-head machine. And because of the strong relation of the 2 strands, we can simplify the notation. Actually, in 2004, it was proven that if we think about the accepted languages, then we can use identity relation. And that means we can just simulate everything with a normal tape, and the expressive power remains the same. All right. So we may have different variants based on biological thinking. Like if we think about that enzymes read these strengths, then we may think about, like, if an enzyme can read something, then we should accept. So, which means that we may have automata where all the states are accepting states. And that type of automaton is like abbreviated with F. Also, we may think about that, what does it mean a state? If we think about that enzymes reading the strengths. So maybe we have no states at all, so which means that actually we have only one state. Then the automaton cannot store anything in its state. So this is called a stateless variant. Or we may think about variants when only one of the head can move in a transition, and that's the simple variant, or the one limited when exactly one letter being read in each transition. And as the first two constraints about the number of states, the second two constraints about the transitions, we may also mix that type of constraints. And we have orthogonal conditions, like if the machine is deterministic, or various other, like I will tell later about these things. So we may think about some, these are still finite state machines, but we can accept some even non-context free languages by the two heads. So here, the market copy language, WCW, can be accepted in such a way that the first head goes when it finds the C, and then in correlated manner, both heads are reading exactly the same thing. And whenever the second head finds the C, it can just finish the reading, but the first head cannot move anymore. So this shows the power of two head in such automata. Another example can be when another well-known non-context-free languages can be accepted, like A to the N, B to the M, C to the N, D to the M, again in a very similar manner. So we go with one head to the position when it reads all the A's and B's, and then we start and check the number of C's and A's together, movement, and then the D's and the B's also together. All right, so now a special variant I want to show, the 5' 3' Watson-Crick automata. So in these automata, the two heads are going to the same biochemical direction because the two strands of the DNA has opposite 5' 3'. That means from physical or mathematical point of view, the heads are moving in opposite directions. So we start from the two extremes. And in the sensing variant, we may think about that we finish the computation when the two heads meet somewhere. So, and in this way, with these finite automata, we can accept all the linear context-free languages. However, the deterministic variant is weaker, and the language class is called 2.lin, showing that it's the counterpart of the linear context-free languages, which can be accepted by the deterministic variant of this two-head automata. So we can think about like that. We have a double-stranded DNA, and now the two heads are moving. So here is like a deterministic automaton which may accept the language of palindromes. So those words which are the same as their mirror image or their reversal. Another example could be the complement of the market copy language when, but here we use non-deterministic automaton. So the automaton is guessing when we have some position where they will not match, and one of the heads go and check this position, and then the two heads are going in the same way, and in this way we will find where is that position on the other side of the middle, what we need to check. If this, and if they mismatch, then we can accept. Otherwise, we say that this non-deterministic computation was not showing the difference. Let it be accepted by other non-deterministic computation if there are some mismatch positions. All right, so here again, we have the many variants, the all final, the one state, the single or the one limited, and various determinism. And also, we may allow when we finish when the heads meet, or we may have the full reading version. So there are some hierarchy here. We may think about that this class of languages are those ones which can be accepted by deterministic machines here. And actually these are with our automata. So the regular languages are here. And yeah, some classical language classes like regular, deterministic, linear, deterministic, context-free. These are there. We can see that the full reading variant can do even some non-context-free languages. And yeah. So I mentioned that there are various deterministic definitions. So we may define the classical determinism when there is at most one way to continue any computation in each configuration, but we may define also state determinism when we have exactly from any state we can reach only one, at most one state. Doesn't matter what we can read or not. And we can also define the quasi-determinism when in each configuration the next state is uniquely determined, although maybe the next configuration is not. So whenever we are in some configuration, it will be clear what is the next state, but maybe we can go to that state reading different things, maybe with the first head or by the second head, and so on. So here is an example. So this is like a quasi-deterministic automaton. Even this is quasi-deterministic finite automaton, so without two heads. We can see that we may read nothing or plus or minus, and either we read a 0 or we read a 1, and we read zeros and ones after. So in this case, the set of states can be partitioned. Sometimes we have deterministic behavior, like here. Or sometimes here we can see that we have the state deterministic behavior. So the same state can be reached, but maybe we read lambda or maybe we read something else, and that's officially a non-deterministic behavior. All right, so finally about Watson-Crick automata, I want to show that we may use them also to work with circular words or necklaces. So whenever we think about an input word, we may think about like not as a string, but like a circular word. And our motivation comes also from DNA, because there are many DNAs in the nature which has this cyclic structure. And from mathematical point of view, usually we think about that instead of words, now we take the set of the conjugates, which means that we start the circle from any point, and like we have the set of all possible words that represent that circle. And yeah, classically we have prefix and suffix. When we think about a circular word, we don't have, but we have subwords. And yeah, we may have languages which is closed under cyclic closure, and those are actually that type of languages which are the necklace languages. So now when we have two heads, it's very appropriate to use it, because now we can start the computation anywhere, and if the two heads are going to the two different directions, then we can accept when they meet, and then we know that the full circle was read. So we don't need to mark anything in the circle. And so now when we think about accepting a necklace, then this is like that. However, we may define weakly accepted and strongly accepted circles or necklaces. Weakly accepted if we have a point from where we start and we accept it. Strongly accepted means that doesn't matter from where we start, we must accept it. So we have two different acceptance conditions because we have like a set of conjugates. If we accept at least one, then we say it's weakly accepted. If we accept all the conjugates, then we say this circular word is strongly accepted. And yeah, so whenever we think about the weakly accepted languages, then those are exactly the cyclic closure of the language class of the linear languages, because with the standard 5', 3' Watson-Crick automata, we can accept the linear languages. Only context-free languages can be accepted in this way, but because the set of linear languages is not closed under cyclic closure, but the set of context-free languages is closed under cyclic closure. Therefore, only context-free languages can be accepted when we use weak acceptance. But it's incomparable with the set of linear languages because like this language is a linear language, but not a necklace language. And yeah. However, when you use strongly acceptance, strong type of acceptance, then we have a much more interesting behavior. So here is a nonlinear but context-free language that we can accept, like A star, B star, A to the n, B to the n, or A to n plus 1, B to the n, or when we start simulating with somewhere else. However, we may also accept some non-context-free languages. And this automaton is accepting, like with this accepting state, we accept all the inputs are in this form because we are checking the number of A's and C's that match. Here we accept everything which starts in this way, with this way. And then if we think about like the cycles which accept it from anywhere we start, then we can see that those cycles are the cyclic closure of A to the n, B to the n, C to the n, which is a non-context-free language, but we have a finite state machine which can accept it. All right, now I'm moving to another large part of the presentation. Why commutations and traces are interesting? Because we can model parallel events or parallel processes. So semicommutation is a mapping when two consecutive letters we may change the order if the order was in the given way. When we think about partial commutation, then it doesn't matter what was the original order, we can write them in any. And when we think about commutative closure, then all the permutations of the words are allowed. So formally, we have finite alphabet, we have the length of the word, we have the number of A's, the alphabet of a word, like which letters occur in that. And we may define a so-called dependency relation, which is reflexive and symmetric. So reflexive means everybody is related to itself, and symmetric means if we have a pair, then we have it in the other order as well. And then we can define the independency relation such that we have like all pairs and we subtract the dependency relation. Then of course this independency relation, which is also called commutation, is symmetric and irreflexive. So yeah, if we think about parallel events, like we have an event A and B, they are independent, which means that like there are two different machines in the fabric which are doing things, and doesn't matter in which order we are switching them on and they are doing their job, the result will be the same. So which means that if we have something like that, this is equivalent to that one. And even we may think about that this A and B things may be going in parallel to each other because the order doesn't matter. So when we write the parallel events in this way, then we use a so-called linearization. And actually, these are what we have here. These are the so-called traces. All right, so traces, we have an independence relation, as I told, also called commutation relation. So A and B are in relation when, if this is in our language, then also the other one must be in our language. And so we think about that. U contains like the preconditions of this process A and B. And then A and B can be done even in parallel or in any order. And whenever we have them, then we have everything which is ready to do the things which are written in V. So the traces are describe such phenomena, and the linearized form is good because then we can use like classical language theory to describe those events. So now if the relation, like the commutation relation, is empty, then we have just the original language. If the relation is full, which means everything is independent with everything, then we have the commutative closure of the language, but we may have various cases between these two extremal cases. So now let's see automata with translucent letters. So we know that the classical automata accept the regular languages, both deterministic and non-deterministic version. Now, in each state, we may have some letters which the automata can't see in the input. So, which means that the automata will see the first non-translucent letter and make a transition based on that. So in this way, the input is not processed strictly left to right, but we will see some tricks. So basically, we have the set of states, the input alphabet, we have a set of initial states, we have an end marker. We may need end marker to see if maybe all the letters which we have still from the input are translucent, and therefore we will see the end marker, and this means that we can decide on what will happen. So we have the translucency relation, so for each state we have a subset of the alphabet, and then we have the transition mapping. This is like the non-deterministic variant here. If we think about the deterministic, that means we must have exactly one initial state, and we have the usual deterministic transition relation. All right, so how it works. If we have an input on the tape, we have the end marker in it. So then the input can be written in such a way that U contains only translucent letters. So A is the first letter which is not translucent. And then we will read A from there, and this will be the remaining input. And whenever we finish the computation, like we can only the dollar sign remains, then the machine decides on the acceptance. So here is, for instance, the DIC language, the language of bracket expressions. So think about that A is an opening bracket, B is a closing bracket. So first, you need to read an A from the beginning. And then all the A's are translucent, and you read a B. And if nothing left, then you accept. Otherwise, it should start again, an opening bracket, and somewhere it has a closing pair, and so on. And so this automaton accepts a deterministic context-free language, which is the DIC language, the correct bracket expressions. What are the correct bracket expressions, just to remember? So we have the same number of A's and B's, so same number of opening and closing. And for any prefix, the number of opening cannot be less than the number of closing. So, and the automaton checks that property. So, yeah, finite state machine. So, for instance, here, this is the input, okay? So we have A, B, 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 A. So in state A, in state 1, we read an A, so this is the first letter. So this gray color shows that this is already not there, this is already red. Now we are in state 2, we need to read the B, but the A's are translucent, so we can see this B, and we read it. Now we read again an A, but from the beginning, and then a B, and then an A, and then a B, and yeah, this is not a correct input, so we will not accept it. So that's a deterministic machine. It says that if you think about that, you have open, open, close, close, then you see in this prefix, there are more closing than opening, so this is definitely not good for us. All right. So now if we want to accept the language which has the same number of A's, B's, and C's, which is not context-free, but context-sensitive language, then in the first state we have that like B's and C's are translucent, here A's and C's are translucent, and here A's and B's are translucent. But here we read an A, doesn't matter where is the first A, and then we read the B, doesn't matter where is because the other letters are translucent, and we read the C, other letters are translucent, and it checks if the number is the same in the input. So let's see an example. So we start from state 1, we read this A, and then now we are in state 2, where the A's and C's are translucent, so we read that B, and then now we read a C, and an A, and the B, and the C, and so we accept this input. All right. So what are rational trace languages? Rational trace languages are those trace languages which can be defined based on a regular language by adding some dependency or independency relation. We see that these are one-to-one correspondence to each other. So, and then for each rational trace language, we can construct a translucent letter finite automaton which accept that language. Moreover, each language contains a letter equivalent sublanguage that is regular. Therefore, we can accept only semilinear languages. The language class is incomparable with the deterministic linear, deterministic context-free, and context-free language classes. But of course, all the regular languages we can accept. We have very nice closure properties. When we use the non-deterministic finite state automaton with translucent letters, then the accepted language class is closed under the regular operations and under the commutative closure. However, it's not closed under intersection, even not with intersection with regular languages, and not closed under complement. But each commutative semilinear language can be accepted. So in the deterministic variant, we can still do all the regular languages, but we cannot accept all rational trace languages. And we have not so nice closure properties. So it's not closed under the main operations, but it's closed under complement. So for the deterministic variant, we have this feature. So how we can think about the word problem? So we can think about that. We do some pre-processing, which means that, let's see the example. So for each letter of the alphabet, we have like a linked list. So we start from the end. Null means no more letter appears. So we start from the end. The last letter is A1. So we say that here is an A1, and here we store like null pointer. And this is where A2, this is where AN, this is where A1, and so on. So we have a linked list. That means the head is showing the first occurrence of A2, which is here. Here we show where is the next occurrence of A2, and null means that there are no more occurrences of that letter. And then to decide what is the first non-translucent letter, we just need to compare these pointers. And so we have easy access for the first occurrence of any letter. So I wrote that. It's like the word problem is like linear time, but it's actually n log n, because it depends on how we can store these pointers. So this is the thing how it goes. So when we erase a letter, that actually we just replace that. We just replace the head with that pointer, what is stored at that point, and we can continue the process. So yeah, this is like when we have an input word and we want to compute if it is in the DIC language, then we can make this pointer list, and then we can easily decide. There are many variants. Of course, we can have translucent letter extension for pushdown automata. Even we may have translucent letters on the tape or translucent letters in the stack. We may have translucent words when we can see not only letters as translucent, but words as translucent. We may have half translucent letters when we may define transition on letters which can be translucent, and it's non-deterministic if this letter is now translucent, or we have a transition and erase it in a step. And we may have the variant when the head stays at the position where it was erasing a letter and not going back to the beginning, and the head will go to the beginning only if it ends the end marker of the word. And yeah, if we have translucent stack symbols, then we have a Turing universal automaton, so it's very easy to simulate a two-stack automaton. Finally, I show jumping automata. So in jumping automata, when we read an input letter, we can jump anywhere in the input, any position. So, and which means that we will read the next letter from anywhere else. So basically, the commutative or the commutative closure of the regular languages can be accepted. Here is a hierarchy when we have here some classical language classes. This is the rational trace languages. Here we have like the deterministic finite automaton with translucent letters, then the non-deterministic one with translucent letters. These are the non-returning variants, and some jumping automaton are here when actually we can jump only to the right and so on. So I was talking about finite state automata, but not the classical finite state automata, but some more powerful finite automata when this power comes that we read the input in non-traditional manner. So we have seen two head when we started from the two extremes, and the linear languages can be accepted. We have seen the translucent letter automata when all the rational trace languages, and also some other languages like the DIC language, which is a very important context-free language. Both with the jumping automata and the translucent letter automata, we can accept easily the commutative closure of regular languages, which means all commutative semilinear languages. So here are some references about some classical multi-head automata results, and then some Watson-Crick automata results, and here are some automata with translucent letters. Yeah, in some papers we used very, very technical names. It's like cooperative distributed systems of stateless deterministic restarting automata with window size 1. So, but that's actually just automata with translucent letters. It's just the history how we found this model. Yeah, these are other translucent letters. So this is some recent work when we had not translucent letters but translucent words. And yeah, some jumping automata are here. So thank you very much.
Just thank you. It's a very nice lecture, and this is like extension of the regular languages. But it's a question that it is handled some larger scale on the formal languages, but there are some traditional. So, what are some applications when it's better to use these approaches than let's say like efficient somehow?
Yeah, thank you. That's an interesting question. And yes, of course, there are applications like so. As I told, when you want to model parallel events, then these trace languages and this finite state machine behind could be very expressive and very good. On the other hand, we also applied some for natural languages, some phenomena in natural languages. Especially in some natural languages, we have like free word order, and then with translucent letters, it's much easier to deal with that type of things as to put some classical device and to try to find all the permutations of the things. So it will be much more smaller the model. I mean the automaton, which can accept the same thing. So the idea is usually here that if you have a finite state machine, then you can do it with really small memory or efficient computation, and we may have much larger expressive power than the classical regular.
Question?
Network, Institute for Computer Science and Control. And now we will sell to somewhat different waves or routers, and we will go to the field of robotic automation. And my presentation will be about the tolerance aspects of digital twin-place robotic solutions. So first, I would like to introduce what we consider like conventional or maybe advanced autonomous automation applications. And for the conventional ones, we can maybe agree that we can consider every input to be there already in the design phase, and based on that we can program our robots deterministically. And there may be some uncertainties, but these are usually can be overcome by compensation, and maybe we need some proximity sensors or something like that to deal with some of the uncertainties, but we can assume that most of the information is there when we are designing our systems. In case for autonomous robotic solutions, which you can see on the right-hand side, these are always missing some kind of task-specific information. For example, in this case, we can see what workpieces we want to manipulate, but we don't know their exact location on the conveyor. So if we consider this as a conventional automation, the tolerance aspect for the location of the batteries would be comparable to the size of the conveyor itself, which is intractable for automation. So we need some kind of on-the-fly, observation-based resolution of this missing information. And basically, we need some kind of sensors, for example, vision sensors, 2D, 3D cameras, and some data processing algorithms, which need to operate almost real time because they are all part of the cycle time during the operation. But this allows us to go to reach out to more automation fields and apply it to more difficult scenarios with required flexibility, with dynamically changing environments, and maybe human-robot collaboration or robot-robot collaboration. So during my presentation, I will talk about robot arms specifically, and I will be using the pick and place as an example, which is a type of assembly process for robotics. And there are two main scenario groups for pick and places nowadays. One is the warehouse scenarios, where these uncertainties originate from the shape of the objects. There are a lot of different products that need to be manipulated. We need to put products from one box to another box and basically recognize these products and try to calculate how to grasp them and put them into another box. So we don't have that much tolerance requirement on the placing side here because the boxes are pretty big, but usually, this may be a problem sometimes as well, as you can see on the animation. The other group of scenarios is the factory scenarios, which are usually much stricter in terms of tolerances because these are coupled with previous and subsequent manufacturing or machining or robotic processes, and they are coupled with them through the tolerances. Usually here we have a much better control on the shape of the products, so we usually have a CAD model or some kind of 3D model to operate with, but the uncertainties in the system are usually poses and exact locations and maybe the placing poses of these processes. Some basic consideration, just to be on the same page with you. In our laboratory, we consider these terminology as I will present you. So when we have a conventional cell, we can perform online programming if we have a physical work cell with the robot already there. So for example, using a teach pendant, by jogging the robot, we can record poses for the robot in the physical cell as target poses or maybe poses to interpolate through. Or if we have the digital representation of this cell and maybe we don't even have the physical one, then we can perform offline planning, offline preprocessing, which is called offline programming. And this gives us the benefit to optimize and verify things already in the simulation, and we don't need a physical cell for that. However, in the end, when we want to transfer from the digital space to a physical space, we need to mesh the two together because we need to make sure that the stuff that we planned in the offline space will be feasible also in the online space as well. For autonomous robotic cells, these two, like online programming plus offline planning tools, are not enough because we have these uncertainties that we need to resolve. So we need some kind of online planner tools in addition to those. And these online planner tools need to be fed using our metrology, our sensor data, so that we can adapt our passes, adapt our graphs on the fly. And we also, because we are usually planning most of the stuff that we can plan in the offline phase, we need to match that also to the online phase to be able to tell that, yes, it will be feasible in the online phase as well. There are other solutions, but I won't talk about those. Some quick words about robotic precision. So positioning precision usually have two components. One is repeatability, which is a variance type of measure, which gives us the radius of the sphere within which the robot will arrive in response to a commanded pose. And we have an accuracy measure, which is a mean type of measure. And repeatability can really undermine offline and online programming because it is really difficult to compensate for that. It's a random tolerance, and it is usually part of tolerance chains. But accuracy can be compensated using calibration, and therefore it is still suitable for offline programming as well with correct calibration. We also have the term resolution, which is basically the smallest joint increment that the robot can make. This will also appear during my presentation. Now, some quick words about the digital twin concept. So I'm sure that you're all familiar with it, but I just want to summarize real quick. So this is a virtual representation of a product, process, or system, or any combination of those. And this is basically a collection of relevant models that are well organized. And this is the physical or the digital representation is synchronized with some frequency to the physical object that we want to make the digital twin of. And this can be used throughout the life cycle of this system for simulation, optimization, verification, etc. And for the pick-and-place scenario, for robotic pick-and-place, we collected the fundamental models that are relevant in most of the cases. The first one is the kinematic model, which basically represents our entire cell geometry, including the robot. So it has the robot forward and inverse kinematics in it. It allows us to plan the layout. It allows us for collision checking. We have a grasp model. A grasp model is for, of course, connecting the gripper to the workpiece and what the relation can be. The path model, which defines the motion of the robot. And there is a subset of that is a servo model, which is when we don't have a geometric condition for the motion, we can apply other types of conditions as end terminators for this motion and use as another motion strategy. We have the metrology model to uncover the uncertainties in the system and update our models and feed the data to the other planners. And we have the tolerance model, which will receive some special focus today to evaluate this closeness between the physical and the digital counterparts. So, a quick overview about the iterative digital twin-based robotic application development process. So, in general, we want to plan as much and prepare as much as possible in the offline space. We don't want to build the physical cell and don't want to occupy the physical cell without it being commissioned. And therefore, we are starting in the offline phase. We are starting with the design step, where we collect all the relevant data. We collect the list of requirements, functional requirements, etc. And these are, as test specification, is forwarded to the modeling, where we prepare all those models that I've presented you in the previous slide. And these models provide a basis for the planner tools, which can be a path planning, grasp planning, etc. And basically, you want to prepare every planning tool as much as or until the uncertainties prevent you to do so. And when all that is prepared in the offline phase, then you want to verify the system, check for inconsistencies, check for collisions. Maybe the layout is wrong. Maybe the gripper doesn't have the capability to grasp the part that you wanted to pick up. So you do all these checks. And if all is well, then you can start implementing your system in the physical space and go to the online development phase. On the online development, you check if the installed cell matches with the digital one, because there may be obstacles that you didn't have in your model, or there may be some cables in there which could cause tangling and collision. Then you have the opportunity to fine-tune your metrology model, because now you are in the physical space and you have real data through your sensors, and you can process it and finalize your processing algorithms. And this can be used for updating the earlier models and finalize your planning tools as well. Finally, you need one more verification, and after that, if that's sufficient, you can go forward with commissioning. Now, with more detail, this is the same picture, just added data, models, and plans. You can see that at the verification stage, there are basically two types of decisions that to be made. One is like a qualitative feasibility. So is the system suitable for the functional requirements? If what you have modeled is the representation of the physical one precisely. And this qualitative check is the first part. Then the geometric part comes, which is the evaluation of this digital twin closeness that I will be talking about. And that is matching the tolerances of the virtual one and the physical system, and analyzing if they are within a feasible tolerance region. And now, with that introduction, I can jump to the digital twin closeness, which is the tolerance representation of the digital twin-based development, and give you this example. So consider this. This is a top view of a workpiece, which is a cylindrical workpiece, and a slot into which we want to put the workpiece after the pick and place process. So after the placing, the workpiece should be within this slot. So as a functional requirement, we can formulate something like that, that there should be a region within which the center point of this workpiece needs to fall after placing. We can formulate this, and this will ensure that our placing will be feasible. On the other hand, we can calculate or estimate or measure the actual region for the center point of the workpiece in the physical space based on the design specification containing our tolerance values, like manufacturing and assembly tolerances, precision values, repeatability of the robot, and precision of the metrology, etc. So we can estimate this region, which means that if the system is set up according to the design specification, we will have a region within which the center point of the workpiece actually will be. And now we have to compare the blue region to the orange region and check whether or not the blue region envelopes completely the orange one. Because the orange one is, the boundary of the orange one is really the worst case scenario with all the worst case sampled tolerance instances. And if we see that the orange region is within the blue region, then it means that in any tolerance cases, after the placing in the physical cell, the center point will be in a nice position and the placing will be feasible. However, if the orange region is somewhat out of this blue region, or maybe they don't intersect at all, that means that there are some tolerance instance cases when the placing application will actually fail and we will put down our workpiece onto the edge of the slot, and it won't fulfill our functional requirement. So what to do in the latter case? Well, we have some possibilities. First one is calibration, and calibration can happen in the model side or in the physical side. So for example, it very much can be a case that we have a robot base in the model and robot base in the physical system which are mismatched. Somehow it was incorrectly installed. Now we have the opportunity to modify the corresponding parameter in our kinematic model and modify the location of the robot base, or we can just adjust in the physical space and put the robot base somewhat, displace it to achieve this calibration. By this we can move the regions around. But what happens if our regions are too, the orange region is too big for the blue region? Then we need to apply some kind of tolerance region growing or shrinking. And this can be done by, easiest case, we just apply stricter tolerances, we apply robots with better repeatability, and in general more precise devices. That is one way. Or we can enhance precision in other ways. For example, we can apply a chamfering. You can consider that there is a chamfer on this edge of the slot that would definitely increase the size of this blue region somewhat, because even if the workpiece falls on the edge, it will fall onto the chamfer and it will be guided into the slot, which will still be feasible for us. And the other possibility is to apply some kind of servo system, which is a condition-based motion strategy, and basically override the, until that point, stack up tolerances to a tolerance which is based on the resolution of the robot, the resolution of the metrology system, and the data processing algorithm precision. That is another way. And well, how to evaluate this digital twin closeness? I will give you an example for that. There are multiple possibilities, but I will show you one based on homogeneous transformation matrices, and this is the scenario for that. So consider this example. This is a semi-structured beam picking scenario. The workpieces are laying on a flat surface. They are separated. They are laying in one of their stable equilibria, one of their stable poses. And we want to manipulate this plastic component from this picking surface into these pallets. And the pallets have like a cylindrical part in the middle, which needs to align with the center of the workpiece. And there are some columns which need to align with the edge of the back side of the workpiece. So what do we know? Well, we know the model of the robot. we know the model of the gripper. We have the picking and placing environments and work holders. We have all those models available for us. We also have the CAD data for the workpiece. So we have a lot of information. What do we miss? Well, actually, because this is a semi-structured beam picking application, we don't know the exact pose of the workpieces. There are multiple types of workpieces, so we don't know their type, what is laying there. So we need to identify the type, the stable pose that they are laying in. And most importantly, for the tolerance calculation, we need the location of the workpieces, which is an X and Y, and an orientation about the Z-axis relative to the reference frame of the picking work holder. So those are our task-specific uncertainties. How do we resolve them? Well, we apply a camera, we put it in the robot, we move the robot above the picking surface, capture an image, and based on image processing, we uncover these uncertainties, which can be then fed forward to the other planar tools. What are our functional requirements? The functional requirement is to put down the workpiece onto the pallet precisely, which means that in between all those aligning features. So, how to evaluate the twin closeness? Well, on a homogeneous transformation matrix basis, we first need to define a lot of different frames, starting with the workpiece. We need to define a reference frame and then a grasping frame. The grasping frame will be aligned with the grasping frame of the gripper, basically. We need to define the robot base frame, the robot TCP frame. The TCP is important because usually manufacturers provide the repeatability for the TCP and not for the individual joints. We need the, sorry about that, we need the reference frame for the picking work holder, reference frame for the placing work holder, and that's basically the main frames. And we can formulate a kinematic chain where the links are homogeneous transformation matrices. So a homogeneous transformation matrix between two frames is just a translation and the rotation combined. And these homogeneous transformation matrices are parametric, and the parameters are nominal plus tolerance values of the dimensions. So we can substitute in the nominal value, and we can substitute in a sampled tolerance value into the homogeneous transformation matrix after our formulas are done, and evaluate where the different objects and frames will be at the very end. You can see the connections here. So the base is connected to the work holders and also to the product, and through the robot, it is connected to the gripper as well. We have some tolerance influencing parameters, which are kind of like operators on our calculation. So first, we need to make sure whether or not a pose specification is available from the design specification, because then we have a tolerance value for that, or maybe we need to uncover it using metrology, and then we need to use the tolerance of the data processing algorithm and the sensor that is provided there. Then we have some leading or guiding features that will align our products, and there will be a servoing which can override already existing tolerance stack-ups to tolerances based on the resolution of the robot and the sensing system. For the pick and place, because this is physical contact based, there are 4 different phases of this operation. We really need to check whether or not, or with which components the workpiece is connected to at the moment. And before grasping, the workpiece is laying on a flat surface. It is aligned by the flat surface, and we uncover its location using our cameras and apply the corresponding tolerances there for the location tolerance. Then we position the robot there. The robot will have a repeatability tolerance in there, and we can formulate this on the 2 sides of this kinematic chain, from the base to the workpiece and from the base to the gripper. This can be formulated like that in terms of homogeneous transformation matrices. I promise I won't show you any more of that. I just wanted to highlight one quick example. So this is before grasping. Now we are activating our gripper and get to another state where basically there is a new physical contact between the gripper and the workpiece, and possibly the workpiece is not connected anymore to the table. So there is a transition in physical contacts, which means that we will be breaking one we will be breaking one contact, one body-body connection, and establishing a new one. And this transition will also have a tolerance that we need to take into account, because the gripper is guiding the workpiece in some directions, but in the direction of the red axis, there can be an additional tolerance because it's not guided there. This also needs to be considered. Now the third phase, we move the already grasped part to the placing position. There is another set of repeatability tolerances that need to be applied because the robot is commanded once again. And then we release the parts, oh, once again, wrong button. So then we release the parts, which means that there is another transition between physical contacts. And that means that we are letting go of the workpiece. So the workpiece is not yet connected to the gripper, and it will get connected to the placing work holder instead. And when releasing, there is also another transitional tolerance that we need to apply, because as you can imagine, when you release a part, it is very likely that the part will stick to one of the fingers, and there will be an additional rotational and translational component in the tolerance chain that need to be taken care of. So when all this is done, then we have a placing tolerance or placing frame for the workpiece, and we have the placing frame on the work holder, and we need to compare those because that is our functional requirement. We need to make sure that these two are close to each other in such way that all the aligning features won't collide with the workpiece, but they are aligning it nicely on the pallet. How can we do that? Well, we can apply a Monte Carlo simulation. We can sample tolerances based on their distributions and substitute them into our formulas, our homogeneous transformation matrix-based formulas. And we can calculate individual points, or we can apply a visual evaluation and transform the shape of the workpiece instead, and check for the worst-case scenarios. And indeed, here we can see that these blue boundaries are the worst-case scenarios overlaid to each other. They are hitting the guiding features, both at the columns and the cylinder as well. So there are some cases where the tolerance stack up or tolerance instances are not suitable for placing, for precise placing. And the nice thing is that we have the opportunity to check the effect of different tolerances as precisions. We can change the tolerance values there and find out how to improve our system so it will become feasible in the end. This is the two scenarios in real life. So when everything is nice and tight and precise, and we are performing the releasing process, and there is not much sticking to the finger, and there is no much additional displacement there will be a nice fit. But if we have some accumulated tolerances, and for example, the workpiece sticks to the finger, then there will be a misaligned placing, which is not suitable, not allowed for us. Now this is basically a tolerance model here. So to overview this whole digital twin-based development, I will show you another case, which is an industrial case, and it will show you all or most of the models and plans that are in this digital twin. And the scenario is very similar, just we are manipulating cable shoes. There is a cable shoe assembly that is happening in the press machine, and we need to manipulate these parts into the fixture of this press machine using the same picking place. So once again, a flat surface, semi-structured bin picking. And what do we have? We have the model of the robot. This is a different robot, but it's no problem. We have the model of the picking and placing environment. We have the model of the workpiece. This was 3D scanned, so this was reverse engineered basically. And what do we miss? Once again, we are missing the stable poses and the locations of the workpieces on the table, so we need to uncover those. How do we uncover them? We are using a camera, once again, moving above the surface, capturing an image, and uncovering the location and stable poses of the workpieces. What is the functional requirement? Well, there is one for placing down the workpiece. The precision tolerance there is quite strict. But we also have other functional requirements, like let it be collision-free throughout the cell because it's quite a cluttered work cell. And there is also one for picking, but those are not the main focus now. So we are starting from the offline phase because we have a lot of models, we have a lot of information already offline, and set up the kinematic model, set up the kinematic graph. This is not to be confused with the previous tolerance model. They are very similar, but this is used for layout planning. This is used for robot inverse and forward kinematics, etc. Not for the tolerance modeling. This is the kinematic graph of the system. And we can prepare the grasping because we have the models, basically set up the relationship between the gripper and the workpiece. We can check both at the picking side and the placing side by combining all the obstacles that are there to determine a good connection for the gripper and the workpiece. And we can prepare the pass up to some point because we can determine a metrology frame, we can determine the placing poses because those are not based on the actual workpiece position, not limited by the task-specific uncertainties. And we can simulate a lot of part locations and calculate their corresponding passes. So we can set up, basically offline, we can set up our online pass planner as well. And you can see how different they can be. And we can also set up the tolerance model offline. This is very much the same as in the previous example that I showed you. This is just cannot be simplified to a 2D case. This is a 3D case, but in this case, we can apply the Monte Carlo simulation and overlay all the worst case scenarios and determine a region and check collisions between the worst case scenarios and the placing work holder to analyze whether it will be suitable or not. And then we need to move into the online physical work cell because the metrology model cannot be finalized without capturing at least some photos of the physical components. So we install the cell, we equip the camera, we capture photos of the picking place and the workpieces. We work out our image processing algorithm to determine the stable poses and locations. And with that, we do that basically for every relevant scene in the pick and place scenario, and then we apply all this resolved information to our model. We put the locations of the parts in the model, and we put also the obstacles there because there can be collisions, so we need to check those as well. And finalize our grasp and pass planning online. We can also apply sequence planning. Basically, we apply the offline planned grasps and calculate, through the inverse kinematic model, calculate the robot configurations, of which there can be more. And then basically from the picking to the placing, we can start planning our collision-free passes. And we can simulate these, we can check whether or not they are indeed collision-free, check their time, optimize them, etc. And if we verify our system for twin closeness, then we can basically execute the program in the real cell suitably, feasibly, with high precision, while maintaining the functional requirements. So this is a really good example for digital twin-based development because we have a lot of models available already in the design phase, and there are a lot of things to verify because of the cluttered workspace. There's a lot of things to optimize because of these complex passes, because of configuration changes, sequence planning. So this is a really well-suitable scenario. But what if life is not so generous and we don't have all that information? And this will be my last case study. And basically, the idea here is that PCBs need to be inspected like used PCBs using a multimeter and a probe, a pin. So we are touching different measurement features on the PCB board, and through the multimeter we are reading out the electric values like voltages, resistances, etc. And for this, we need to put a measuring probe onto our robot. So we put a probe there, which has a pin, which needs to be connected to these measured features. And basically set up a system where using these measured features, the robot is able to navigate above a measured feature, and then feed forward and establish a galvanic contact to measure the corresponding parameter. So what do we know here? Well, we know once again the robot model. We know the geometry of our end effector, basically. And we know the environment that we are operating with. But that's basically it, because we don't really have any more information, because this is use PCB repair, which means that manufacturers won't give you the CAD model. And even if you can get an accurate representation, 3D representation of these PCBs, they will only work for a single part, because there are different manufacturers, different production years, and even if you have a single workpiece type, instances of that workpiece type will be visually and geometrically different, so you cannot digitalize the system very well. Also, there is a really high flexibility that is required, because there are really small batch sizes for this type of robotic inspection. And these are PCB products, which means they have manufacturing and assembly tolerances. And the target features that need to be measured are so small, like a couple of tens of millimeters in size, that the manufacturing and assembly tolerances are comparable with those, and not to mention the robot repeatability and all the other components in the system. So it is really a big challenge. You can see here some differences between two instances of the same workpiece type. So you can see that there are geometric and visual differences. So you really can only hope to digitalize the target points as 3D coordinates and not the entire 3D model of the product. So yeah, well, we have some information, and we can start analyzing the system in the offline space. And basically, we can have some estimates. And you can see here that for the functional requirement, because the functional requirement is basically setting this pin to be a galvanic contact with the measured feature, then we have a feasible tolerance region of that size. And if we estimate in the fixtured case, and I haven't talked about that, they didn't even want to apply fixtures, then still we have a deviation region which is in the range of millimeters, so they are not comparable. And if we are considering a fixtureless case, we have centimeters in tolerance. So clearly, we cannot handle this situation using just by calibration means. We need some kind of tolerance enhancement. And for that, we have chosen visual servoing. We put two cameras on the head, on the measuring head, onto the robot. And basically, just in a nutshell, we identify the axis of the pins, and we identify the position of the target features. And using the camera image, we are conditioning the robot to move in such a way that the two of those features get aligned. Here is the quick diagram for that, and you can see it in operation. So that is how we enhance our tolerances, and basically shrink the size of the orange regions to the size of the region defined by the functional requirement. And this serves us as a servo model, which is part of our path planner, and we can apply this in our digital twin to achieve the twin close that we desire. You can see here the operation, so you can see some incremental changes in the positioning of the pin, and then once the precise alignment is reached through this condition-based motion strategy, then we can feed forward and establish the galvanic contact to fulfill our functional requirement. So how do we digitalize? Well, basically, we just record TCP poses for the TCP is the tool center point of the robot for all the features. You can see some different feature types here. And these are just estimated like imprecise positions. But we are storing together with those 3D positions, 3D geometries, two camera images and the target pixel corresponding to the camera images. So what is the target feature? It is described in this visual representation. And using this, we are able to this is fed to the servo model in the digital twin. And using this digital twin, it is possible to transfer all the data to another site, another work cell. And basically, just by showing a process here, basically, they are recording a lot of these workpieces and these target features in Hungary, and they are only doing it once for every product type, so not per product instance, just by product type. And those digitalized product types are then transferred to other countries, other continents, and there are multiple cells that are set up in this way. And just by aligning the reference frames, we can execute the robot program feasibly in those cells as well, based on our original digital twin, which is a huge benefit on the digital twin and twin closeness and precision enhancement side. Finally, some quick recap. So we have talked about conventional and advanced autonomous robotics. The main difference being that the task-specific uncertainties are present in the advanced operations, and for those we need some kind of observation-based online adaptation. We have talked about the digital twins and corresponding relevant models for the pick and place. We have talked about the digital twin closeness, which allows us to plan everything in the offline space and then make sure that that is executed in the online space without any additional adjustment or tweaking in the program code. We have talked about the tolerance model, how to evaluate such a case, and we have talked about deviation reducing methods like calibration and also precision enhancement and the power of servo tools, which can really enhance and reduce the tolerance stack-up to the precision of the metrology system and the data processing algorithm. Here are some references, and with that, I thank you for being with me, and thank you very much for your attention. What do you mean by models?
Like we see the different model for kinematics.
So they are feeding each other. So the kinematic model is the backbone of the whole situation. And based on that, in the kinematic model, there is the model of the gripper, there is the model of the workpiece. And based on that, you can create the grasp model, and then you can create the pass model. So they are interconnected. But yes, separated in some ways. They are different representations.
And I guess each of them brings in some space for errors, like they are precise. And how do you transfer this? How do you represent these possibilities of errors? Because you have to transfer this data, I guess, from one to the next.
Yeah, well, all the tolerance-related aspects are part of the kinematic model. So the grasp model. There are some additional, what I've mentioned, like transitional tolerances, but all the manufacturing and assembly tolerances and like repeatability, etc., are contained in the kinematic model. So you can, these are the kinematic model is parametric, and you can adjust these parameters, and tolerances are part of the parameters. And then you put it into the grasp model, where you enhance it with the more intricate tolerances, like letting go of the workpiece. But one thing is only represented once in the model, so there are no redundancies in between. Thank you.
Questions? No? Okay, now we're here with coffee break, and we will continue at 11.
Thank you. Okay.
Before we move to quickly, you can find some flyers for upcoming events. Please feel feel free to get some flyers from the table. Thank you.
presentation is going to be a bit different, since I promise it doesn't have too many formulas, mathematics. I'm going to try to infect you with the virus of trying to build brain-computer interfaces. So, first of all, my name is Alin Brândușescu. People call me Ozzy. Doesn't have any link with Ozzy Osbourne. It has a link more with OZNE, which means UFO. I am affiliated with Electrobit Automotive Romania, where we develop operating system for automotive industry. My other two are my companies, two startups, one in software development, one in recycling. You can find me at alinbrândușescu.org or over the email. So if you have any questions after that, please feel free to drop me a line. So why brain-computer interfaces? I know how you are, but for me, I was always wondering how my brain works, what makes me who I am. And in the same time, I'm an engineer. I'm not a psychologist, I'm not a medic, I'm an engineer. So the closest thing to understanding the brain is doing something with engineering and the brain. And this is how I arrived to the brain-computer interfaces. But I was not the only one fascinated with the brain. This is an old disease from the ancient times. People were wondering what the heck is with this small white thing in our head. In the ancient Egypt, they were thinking that it's a kind of radiator. So it's just shedding the heat. And that's the reason on the mummies, they were taking the brain out. And things change a little bit on the Antiquity, where Romans with Galen, they decided that after this, taking out the brain of the gladiators, he managed to see that some parts of the function of the perception and the movement are associated with the other types of the brain. Unfortunately, the Greeks, they were thinking that it's just a cooling system like the ancient Egyptians. And that view on the brain kept propagating till the medieval time. But there were some other things in long time ago, 7,000 years ago. Some people dug some holes on the head of a person. Probably the reason is more mystical than theoretical. Probably they wanted to let the spirits go out of the brain. But they were aware that something is happening there. Then Galen, during the dissections, he discovered that inside our brain we have some holes. And for many, many hundreds of years, they were comparing the functionality of the brain with the functionality of the heart, where the heart is pumping the blood through the system, and is, in the same way, the brain is pumping the liquid from these two holes discovered by Galen into the muscles and is creating the movement. But later, through the ablation, by digging holes on the brain, they discovered that by hitting specific areas of the brain, the function of the, usually these experiments were done on animals, the functions of the animal were impaired. And then they start realizing that some parts of the brain are associated with specific functions. And this was even more obvious after Broca's brain. Broca had a patient who lost his speech. And he was able to understand, but he was not able to reproduce the speech. And after the patient died, he took out the brain and discovered that there is one area of the brain which was damaged. And that's the area associated with the speaking. And from that moment, we went in the era of localizations. So after that, they start mapping, the doctors and scientists, they start mapping different areas of the brain to different functionalities. And that was till a couple of tens of years ago.
But let's go back to the brain. So people were fascinated about the brain, how it's working, what it's doing from ancient times. But they had different theories, but now we know more. So what do we know? The brain has a typical weight of 1.2, 1.4 kilograms. Not much. It's really small. But it has between 160 and 100 billion cells inside. And the most interesting fact is that it's using 20% of the energy produced by our body. Pretty cool, huh? 1.2 kilo, 20% of the energy. So if you have, like me, the perfect shape, 100 kilo, that means 12% of your body use, not 1.2% of your body use 20% of the energy. When I read this first time, I say, oh, cool. I'm not going to the gym. I'm buying more books, learning more, and I will lose weight. Is it working? No. Unfortunately, no matter what we are doing, we are sleeping, we are challenging our mind as hard as we want, we are not going to use more energy. So it's stick to 20%. I'm really sorry for that. Out of these 160, 180 billion cells, almost half are neurons. Neurons are the most important cells for who we are, because that's the place where everything happens. When you look on a scan, 40% is gray matter, 60% white matter is how the neurons are structured on the brain, and it's the body and the axon, they have different colors. As I said, there were localization. It started already from the 19th century, and then we start associating different areas of the brain with different functionalities. Okay, we have some physical description of the lobes. If you have to deal with brain-computer interface, you have to know a little bit about the structure, this structure. You have to know what's the parietal lobe, what's the frontal, what's the occipital lobe, where is the visual cortex, things like that. So you have to. These things are localized. So the visual cortex is always on the back, on the occipital lobe. But we are going to come back to this. Many theories in the past, we have to take care not to fall back on the pseudoscience from the beginning of 20th century, when they were trying to measure the shape of the head to localize the intelligence. No, it's not like that. And yeah, there are some simplistic view that you have a dominant hemisphere, which is make you artist or make you scientist. These are really simplified view, not really connected to the reality. So during the 19th century, beginning of 20th century, everything was localized. You had a specific area, visual cortex is here. It's just doing visual cortex processing. And if one area is damaged, it's gone. That part is gone. In big, it's true, but not exactly. It was a big fight, and the research community refuses to accept that the brain is changing its pattern. And the neuroplasticity, it was received with a lot of fight from the research community. So they define an area, which is for speaking, one area for controlling your left hand, and so on and so forth. And they didn't want to accept that that area can change. But it's changing. And why is this important for brain-computer interfaces? Is because brain-computer interfaces can help people change their brain wiring, their brain structure. They can help people to learn new functionalities which they have lost. Just a couple of things about the neurons. So 50% of our brain is, as I said, is made out of neurons. It's 86 billions. You can find different numbers between 7 and 110. Depends on the book you read. There are a couple of types of neurons. The typical one is multipolar neuron. There is a bipolar neuron, usually for the muscles control, especially for the heart. and one neuron has around 10,000 connections. So you imagine 86 billion, each neuron, 10,000 connections, how many connections we can have. Usually, these connections are developed at the, on the initial, after you are born. And till the adolescence, you start losing, and especially during the adolescence, you start losing out of this connection. So losing the connection is good. You don't want to be always super hyped about everything. So, not bad. And the neurons are connected between each other in two ways, chemical and electrical. So the electrical, the axon and the dendrite are directly connected, and it's electrical connection, so electrons flow through. These ones are fewer, and they are controlling especially the muscle, the heart muscles, because you don't want any delay there. So if your muscle, your heart has to keep the beat. The other neurons are using chemical synapses. Chemical synapses are more complicated, and we are going to talk a bit about them a bit later. But except neurons, in our brain, we have another 90 billion other cells. So we have what's called glia cells. We have different types. I'm not going to enter in the details. But each of them has different types. And some of the glia cells are providing support for developing neurons. You know about the myth that after you are born, you are not going to have more neurons. That's false. We are developing always neurons. Very small numbers, but even when you're in your 60s, new studies are showing that you're still developing neurons. Not many, but they are still developing. And that was a myth that is not happening. And another big myth, it was the one which says that we are using only 10% of our brain. No, we are always using all our brain. Just few people seems that they are using only 10%, but just seems they're still using their whole brain. Not going about the cells, but going about the chemical synapses. If you want to have a PhD, you can have one only about this part. Because the processes are so complex, and it's so much about chemistry, electric charges, and you can do it only by looking here. And in this small hole between the axon and the dendrite in the synaptic cleft, a lot of chemistry is happening. And this chemistry can be affected by substances, like, for example, the alcohol, which can increase the GABA and inhibit the glutamate, making the brain work slower, even that we have the impression that we are much faster when we drink some alcohol. In fact, our dendrites, our synapses are not working properly. But in the same time, alcohol is triggering the reward system to release dopamine. So that's the reason we feel so good. Cocaine increases the activity with 300% in the synaptic cleft. But in the same time, video games are increasing it with 75%. This is just fun facts. But why I'm talking about chemical synapse is because with non-invasive brain-computer interfaces is the electrical signal we are recording. So the EEG, and we are going to come back later to EEG, is going to record what's happening in here, in the synaptic cleft. But it's going to trigger that for hundreds of thousands of neurons. So we know that we have neurons, we know that we have some other cells, and we have some ways of recording what's inside our brain. And the most typical recording imaging of the brain are MRI and CT. The typical one, MRI, magnetic resonance imaging, where you can record the structure of the brain, and CT, computer tomograph, again, recording the structure. And positive emission technology, where you see the functionality, how the flow of the blood is to the brain. Unfortunately, the PET and CT are invasive, so are not recommended. You have to do that only in case you are really suffering of a bad disease. MRI is not, so you can have as many MRIs as you want. It's no harm. It's just going to be expensive. But on top of MRI, they develop functional magnetic resonance imaging, and they are measuring basically the flow of water inside your brain when you're performing different activity. And in that way, you can see what areas are active when you're performing a task or you are thinking to something else. But this one is slow and expensive. You can build a brain-computer interface with this one, with an fMRI, but it's prohibitive from the financial point of view, and also from the space. I believe all of you know how big is an fMRI, or typical MRI machine. It's a huge magnet, so. But there are other type of recording which are not so expensive. And the price for these technologies is even decreasing very fast the last years. It's the magnetoencephalography and electroencephalography. You have them on the right, where they are recording from the surface of the scalp your electrical activity. As I said, this electrical activity is basically what's happening in the synaptic cleft in the chemical synapses. A newer one is functional near-infrared spectroscopy. I haven't touched any of that. I still want to get one of that machines. It's nicer than EEG, but it's slower. But you can get more activity, which areas are more active, but much slower than EEG. Because we were talking about this brain imaging technology, this is an fMRI. Who can guess what we have here? So this is the brain scan of two women. The top one is in her 20s, and the second one is on after the menopause, both sexually aroused. So we can see what effect has on the brain the aging. And what do we have here? Here is an EEG recording of a man masturbating on the middle. So we can play some dirty things with the technology too. For brain-computer interfaces, the most used technology is an electroencephalography, and it's basically recording the electric activity of the neurons. It typically has a frequency between 1 and 30 hertz and an amplitude between 20 and 100 millivolts, so it's very small, and not many frequencies inside. So seeing that it's between 1 and 30, you realize that cannot be much information there. But this is important to understand, because again, some myths from the urban legends that you can read the mind with the brain-computer interfaces. No, you can't. Not with this kind of non-invasive technologies. So you cannot read the mind of anybody with a brain-computer interface. You can detect some patterns, some artifacts, but not reading the mind. And processing this kind of electrical signal is quite complex, and we are lucky that in the last years there was a lot of development. The problem is that the brain is protected by a lot of other physical barriers. We have our skull, which is going to attenuate the signal from the neurons. We have also the cerebrospinal fluid, which is going to be between the skull and the brain, which is also going to attenuate. That's the reason we get so small amplitude of the electrical. Even if you record the electrical activity of 100 millions of neurons. You can get much better resolution. You can get much more data if you open the skull and introduce the electrodes there. But honestly, I don't recommend it. I think it's painful. Unfortunately, there are some people for whom could be the only way to communicate. So this is still going to be used in some cases. But for us, for me and my other colleagues, we are using non-invasive electroencephalography for brain-computer interfaces. And that's not painful. Sometimes you must use some gel. So after that, you're even looking better. And probably you are going to see Aurel later using some gel. So looking much better, looking awesome. And there are many, many types of electrodes. When I first used brain-computer interface, 1 EEG, the electrodes were quite big, and you had to apply a lot of gel and scratch the head to get the grays out to be able to have a better signal. But the last 20 years, there were a lot of developments, and you have now dry electrodes. You don't have to use any gel, so you are not going to look awesome after that. Sorry for that. But a lot of things happened. And this happened especially after 2008, when the European Commission launched the BRAIN project, and they were funding a lot of companies around Europe, and also the US had a similar initiative and founded a lot of companies doing research on this area. Yes, so they are wet and dry. You have a typical diametric is 10 millimeters, so imagine how many neurons are around that, inside your brain around that area. Somewhere between 30 and 500 million neurons under one electrode. But OK, so you can record from the head, but how you make sure that if you record from ReLU, from there, or from somebody from here, the next day you get the same results, and you can reproduce the same thing. So for that reason, they standardized the position of the electrodes, because otherwise it would have been impossible to reproduce the studies or to reproduce the treatment proposed using the EEG. This is called the International 1020 system. It was standardized in 1957 and used some anatomical landmarks I showed you earlier on a slide for positioning the electrodes. Looks good. You have to agree with me on that. So with the electrodes, you can record some signal. As I said, the signals are having a frequency between 1 and 30 hertz. And they were categorized in some rhythms. And this happened during the, I think, let me see, 1950, where almost all of them are already categorized. You have the alpha rhythm, which has between 8 and 13 hertz. And it's usually recorded on a healthy person when he has the eye closed. When you open the eyes, this rhythm is attenuated, so the amplitude is going to be smaller. And if you don't detect this kind of rhythm on a person which is healthy, on a person with the eye closed, it usually indicates some pathological problems. Can be even some hepatic disease. Senility or drugs are also attenuating the alpha rhythm. We have beta with a frequency bigger than 14 hertz, very small amplitude. This one is good. If you record this, means that person is really thinking. It's not using TikTok. If you use TikTok, this rhythm is disappearing. So don't use TikTok. Vote with beta. It's not affected by the eyes, but it's affected by muscles and affected by some medicines like diazepam or barbiturica. You have theta, usually it's big on when you're sleeping. So when somebody has theta, big theta is sleeping. is mostly in the frontal lobes. No, if present on frontal lobes, can, on a awake person can raise flag of severe lesions, so it has some problems. Probably it's good to have a CT. It's a good sign. So don't do a CT directly. You just do use this. It's an order of magnitude cheaper and non-invasive. And delta is usually not present except for adolescents. So these are the typical RIMS. The medical professionals, when you go to the hospital and you want to monitor, they are going to record and going to analyze, and based on that, they can detect that you use some drugs or you have some problems. Not so interesting for brain-computer interface. I just use them here because I could say some good jokes about drugs. For us, are more important the one you see in the A, which is the mu rhythm, which is associated with the motor cortex. This is important because the mu rhythm means you are trying to move your hands or do some motor activities. B is usually associated with intellectual activities, even watching TV or reading a book. Okay. C is when you wake up, you can detect this kind of things. So what A is important for us. Another kind of signals is event-related potentials. There are a couple of them. They are appearing when you, as a response of an interaction you are perceiving. And for us, the most interesting one is P3. It's basically P300. And this is really a response when you see something, or you feel something, or you do a cognitive task. Even if you do a cognitive task, you can get a P300. P300 is the P3. Why is P300? Because it usually appears after 300 seconds after the event. It's not exactly 300, it's between 250 and 500 milliseconds. And it's also used for lie detection. So if somebody records you, don't lie because it can be seen. They are not using the polygraph anymore in US. They start relying on P300 because you can see some patterns. There is even one pretty cool test. It's called the Blondie test, where you show images of women and you see to whom the man is more attracted, and the other way around. And that's also measuring the P300 and the amplitude of P300. We have another type of waves we are interested on is visually evoked potential. These kind of waves are appearing as a result of a visual stimulus. When you see something, you can get some signal like this. And the important one is the frequency of these waves. And we are going to talk a bit more a bit later. So we have this signal. These signals are analogical. We are all using computers, a brain-computer interface. It has to go from the analogic to digital. There is some analogic processing, and here were a lot of advances. Though on the new things, the amplifier is already on the electrode to reduce the artifacts for the transmissions. Not going to enter in details, but there is a lot of magic happening here. You can also have a PhD on this part. It's enough still to do. After that, things are quite standard. You sample the analogical signal. You quantizing the signal, and then you are encoding and send it to the computer. Not much. This is what's happening. You take the samples. If you study electronics, you probably got a lot of classes on this, how is the best to sample. Seeing that we have only 30 hertz, probably the sampling rate should be bigger than 60 hertz. Currently, there are some brain-computer interfaces coming to 250 hertz. They are trying to see if we can get more information on the other range, but typically it's 30 hertz. And if you increase, you have to know that you have to increase the sampling rate. So again, some nice part if you want to study. But OK, so we have this signal, we digitize it. Can you see something? Can you understand it just by looking to this? Some medical professionals, after a lot of training, they can see these details. But we are living on the era of AI and digital processing, so we can do more than just looking by eye on this data. And usually, we do some transformation from the time to the domain and looking on the frequencies, which is giving us much more information. These are the only formulas I put here, and I don't remember them. You have RDTs in the library. And one of the questions I always ask people coming to the interview, what function you use to sort an array? And the correct answer is only one, the library function. You don't implement yourself the same. You don't implement your fast Fourier transform, you just use something already implemented. Only if you're a bit masochist, you go here. Okay. So this is about what's brain, what's the signal there. Let's look now what do we have to do to get a brain-computer interface. So we have to acquire the signal, we have to digitize the signal, and we have to have a translation algorithm to do something with that output, and then to create a command. This is the typical, and if I remember well, this is from an old paper from 2002, and not much changed. Everything stays the same here. What's inside the boxes can change, but what changed in the last 10 years is what you do here on this area. How you use the output. Now, one back. For EEG, brain-computer interface, non-invasive one, there are a couple of types of brain-computer interface. One of them is based on motor imagery, and this relies on the fact that when you move your right hand, your left area of the brain is going to get more neural activity. The same, if you move your left hand, your right area of the brain is going to get more activity. Funny thing is that this is happening not only when you move the hand, but also when you imagine that you're moving your hand. The activity increases on the other side of your brain. Yeah? So based on this, you can detect the willing of moving the hand left or right, and you can create a binary brain-computer interface. This is happening by recording the activity on the parietal area. So that's the reason I put that picture showing you the area of the brain. I also put the international 1020 standards to see where exactly the electrodes are placed. Another type of brain-computer interface is the P300. This is a class of brain-computer interfaces because they are three types, at least three types I have used. One is visual. You are watching something on your screen and trying to focus on your interest area, and then you can detect what area you are interested in. This is the, the visual P300. And you can see the speller outside. So my colleagues from Timișoara are here, and you can just go and have a look after before the lunch or after the lunch. Then there is a vibrotactile P300. In this one, you are going to get some vibration on your left and right hand or other parts of your body, and you try to focus and count the vibration where you're interested on. For example, if you have left and right hand vibrating, you are trying to count the vibration from the right hand, and then you can detect that you are counting the one on the right. Because you are going to synchronize the vibration, and you can detect when the P300 signal is happening. So in this way, you can have also binary yes/no activity, brain-computer interface. Another one is auditory. These are different types. You can have stereo environment where you put sounds on left and right, or you can have different pitch tones or different beeps. And again, the person has to count the interested beep or the pitch, and then you can detect which one is counting, and you associate yes, no, or action with that counting. So I forgot one, I believe. There is another one, and I think I missed the slide. I don't have a slide for it. It's steady stimulus, visually evoke potential. You are focusing on an area flashing on a light source. And if that light source it has a flashing frequency less than 20 hertz, you can detect on your visual cortex that kind of visually evoke potential. You can detect the same frequency. And then if you have, let's say, four boxes, each of them on the screen, each of them flashing with a different frequency, usually between 7 and 19 hertz, you can detect which one you are focusing on. And it is where you can create some commands, and you can move a cursor or do some selection of actions. There were a lot of developments in the last years. The first time I was using a brain-computer interface was 2007. And it was a big amplifier with a lot of cables. You had to be prepared. Everything took half an hour at least to use it and calibrate the system. Things changed. Now you can have one, and you can just wear it, and you don't have to be tied to any amplifier. The amplifier is miniaturized. The price is 10 times. Okay, the quality is not exactly the best, but still, it's amazing how much happened in the last 15 years. It's easy to use. There are a lot of development tools for developing applications for brain-computer interfaces. But why we need brain-computer interfaces? Brain-computer interface is very slow. If you paid attention, I said that you can have, for most of them, binary, yes, no, 2 actions. For SSVEP, you can have more, 5, 6, but not more. So the communication rate is very, very slow, very small. But why we need it? Because communication. And communication, not for us. We take the things for granted. We can speak, we can see, we can move. But there are people who are suffering for some terrible diseases, and for them it's impossible to communicate. There are people in vegetative state, or unresponsive wakefulness syndrome, or minimal consciousness state, or people affected by multiple sclerosis, or locked in. These people cannot communicate. Okay, and it's terrible. Imagine for yourself to be in your body and to be aware of everything around you, but not to be able to communicate. So for these kind of people, the brain-computer interface can be the only way to communicate. And I believe everybody knows Stephen Hawking, and he had still eye movement. So he was not using a brain-computer interface. He was using eye-tracking devices, but there are people who are even worse. And in the last 7 years, especially for a vegetative state or unresponsive wakefulness syndrome, they managed to communicate with people who were considered in deep coma, and they were ignored. And there were some success stories where they managed to take people out of coma because they were aware that the people are inside and are awake inside. But it can also be used for these people with disability to control the robots, to increase the quality of life of the people with disabilities. And this is something that we have done in Timișoara a lot, because we try to develop a lot of games for people with disability just using a brain-computer interface. So for rehabilitation, there are also some nice successes for rehabilitation where, based on neuroplasticity, on the fact that we know that our brain is changing, we can provide feedback to people to increase their activity, to perform the task better. And there is one company in Austria which has some impressive videos with the improvements done by some people suffering of multiple sclerosis. And yeah, there are some also atypical, like prisoner evaluation, like I said, lie detection, or stress assessment, as Ioana did a study last year, seeing if the students are stressed when they see the classroom during the exam session. And who can help? I think all of us can help. And one story, so all of you has now a smartphone. Everybody's using Facebook. But before iPhone and Android, there was Nokia, and it was perfect, cool phones. And there was Hi5, which had the same network of friends, messages, pictures. Why they disappeared? Who knows? Better quality of the iPhone? The wall from the Facebook? No. There was something totally different, and nobody's noticing. Both of them did something special. They released their API public, and they convinced developers to come in to create application. And this is what we can do. We can try to create application, to innovate, because we have the basics, we have the electronics, we have the recording. But what's missing is something which can be useful for people needing these kind of devices. So all of us can help. And that's the reason I advise everybody to get involved on this, because it's pretty cool and can help people. And also, I'm not affiliated with any of them. I don't earn anything from them, but just put it here to see that the prices for a brain-computer interfaces are really small. So even a small company or a university can afford to buy such devices and experiment with. And after the next presentation, you can find my colleagues on the hallway with one of these brain-computer interfaces. You can talk with them. We have some videos with the games developed. They earn around 5 prizes on some international hackathons. And tomorrow, some of them are going to present about their success and the games they developed and how was done and what were the challenges. OK, that was all from my side. And I hope I managed to infect at least some of you with the virus of brain-computer interfaces.
Very, very interesting talk. Are there any questions or remarks?
Where we are in the development of this interface, you mentioned that there is 10 centimeters and it covers
50 million.
Millions of cells. Do you want to reduce the size or to have smaller devices? Or is that a good direction, or what kind of development we can expect?
Honestly, I'm not expert on that area, so I cannot know. I don't know. You can ask the guy from GTEC. They are in Austria. They are working on that part. And what was done in the last years to move the electronics inside the electrode, so the amplifier, not to be just a simple electrode, but to have an amplifier inside, to stop losing the
noise.
Yeah, not being affected by the noise, not losing, but not being affected by the noise.
Thank you.
Other questions? Thank you again.
Thank you.
Próbálok.
Ugyanígy eljusson a hangozat.
Mert lehet viszont, hogy akkor átülök ide, ha nem gond.
Nekem az is jó, persze.
Be vagyok rekedve nagyon.
Jó, ülj, és akkor Tibor
nem baj.
Tök jó, miért lenne baj?
Tibor, cserélj majd, abba vagyok, hogy Tibor cserélj a hangot.
És meddig is mész? Meddig van az idő?
Jó? Nem baj, ez van szerintem.
Ja.
Hosszú volt, de nem értem végén.
Először majd meg kellene egy mondattal mutatkozzatok be, jó? Nem tudom, mindenki ismere itt mindenkit. Csak elmondjátok, hogy mi a background, vagy én mondjam el? Jobb, hogy ti elmondjátok. És aztán majd kezdjük azzal, hogy mennyire nő még ez az exponenciális növekedés egyáltalán, illetve mi ennek a szociális hatása, jó?
Lehet, hogy jobbsabb, hogyha te mondasz egy nincs.
Én nem tudok rólatok semmit. Rólad különösen nem tudok milyen. Pozitívat semmiképpen. Pozitív? Hát egy nem negatív. Ja. Nem negatív és nem is. Okay. Ladies and gentlemen, this is a round table. Actually, this is a rectangular table, but mentally it's a round table about artificial intelligence. And you have seen many technical aspects in the past presentations and the upcoming presentations as well. Now we will talk a little bit about other aspects, like social aspects, legal aspects, and maybe philosophical aspects of artificial intelligence. And I would like to ask, I will moderate this round table. My name is Miklós Hoffman, I'm the Dean of the Faculty of Informatics in this university, and I would kindly ask my colleagues to introduce themselves in a few words.
Thank you. I'm Benedek Nagy. In this round table, I will be the role for the philosophical and mathematical and theoretical side.
Okay, my name is Péter Molnár, and I'm a senior lecturer at the Károly Gáspár University of the Reformed Church. Basically, I'm a lawyer. I'm working at the. Okay. So I'm working in the Department of Public Administration. So that's all for now. Tibor?
I'm Tibor Tajti. I'm working here in Faculty of Informatics. Basically, I'm researching and teaching machine learning. That's why I'm here.
Okay, so as you can see, we have one theoretical person, one experimental person from the AI side, and we have one person who represents the society, the rest of the people. Okay, and I would cite a sentence from a scientist, and it is actually it's not about AI, but we can understand it as it is about AI. Technology changes exponentially, but social, economic, and legal systems change only incrementally, linearly at maximum. I would ask you at first about the first part of the sentence. Technology changes exponentially. Is it still true for the AI that the capacities, the abilities of the AI still change exponentially nowadays? Maybe.
As far as I know, yes. Basically, the Moore law still applies. That means that in every 18 or 24 months, this was the law, doubles, the capacity is doubling. And if we add that also the models are improving, that means that this capacity, this improving capacity will be used more and more efficiently.
So it's doubly exponential.
Yeah, and maybe one more thing that, for example, there is one benchmark which is not very scientific, but somehow they try to measure the current AI capability. How many human work can be done by the AI consistently in a row without human intervention? And it was said that it was also doubling in every 7 months, but now within 3 or 4 months it went from 54 minutes to 7 hours, which is not doubling.
Okay, I don't know if you have any.
I could answer more of the second part of the question, but what we see as lawyers, we are saying that the same as Tibor, that more and more applications appear month by month. So we have to follow somehow, but I mean, that's all for this part of the question. And then we
for this part of the question?
On the other part.
Yeah.
Thank you.
From theoretical point of view, nothing can continue their development exponentially forever. So it must be somewhere a point when we can try to smooth.
On the one hand, that could be true. On the other hand, maybe it developed already too much, and maybe there are already too much AI, and I'm not sure that if there are really so many human jobs that human need to do what AI is doing instead of the people now. I mean, maybe we are using the AI to do many things which are totally useless and we don't need at all. And if we do this acceleration, then it will do more and more things that we don't need, but we are just using our environment. And you know, my first interesting point is that if we have billions of people in the earth, why we don't need to speak with each other, instead why we want to speak with an AI? That's our...
Yes, you may refer to the fact that, for example, those ChatGPT, for example, those platforms are used mainly for bullshit. I mean, for asking a recipe or just talking about nothing serious.
I mean, if somebody needs a recipe, then it could be okay. But many people just use it because they think it's fun, or they think that if the other use, then I use, or they are lazy to do their job, like homework, and therefore they are asking ChatGPT to do something, and they submit without even reading what is there.
Should we regulate the free usage of AI, like AI-based chatbots or something? Should we say something that not everyone can use it for everything?
It's a hard question.
Yes,
and
it is.
I think it's... So basically what we have to say, an act on AI, even the European Union's AI Act, won't answer these questions. These questions will be answered, and all questions of the law according with artificial intelligence are answered in the actual law system, in the actual legal system. I think maybe we should, but as a lawyer I can't say that we can, because I see no legal possibility for that.
I mean, historically, if you consider the driving license, okay,
Yeah.
it allows you to drive on the road. It was not trivial that you need a driving test, for example, for a driving license. For many, many years, if you wanted to drive, yes, you can drive, or you were able to drive without any preliminary test. I don't know if you know what was the last European country who introduced the driving test for, obligatory driving test for a driving license. No idea. Belgium in '77.
Oh.
Which means that, yeah, that's surprising. Analogously, can I suggest something like a driving license for AI?
Okay.
That you must use it responsibly. You must drive on the road responsibly without harm.
I think because AI is behind every emerging technologies.
Yes.
For example, it's in the social media, and it's behind the social media. It's behind many things. It's behind the cars you drive. It behind everything. Maybe it would be good if we had some kind of driving license for AI, but we do not have, because if we need a driving license for AI, we should need a driving license for all the use of the internet and computers and everything, you know. It's too interconnected. You cannot separate those things.
I see.
I think that yeah, it could be possible, or maybe it would be good, but maybe some other things would be more important. For example, people should have a driving license to vote.
So actually, it was an idea to have like not driving license but computer license, and you shouldn't use computer without having any knowledge about computers. But the problem is that there are companies who wants to sell computers, and they don't care if somebody has any knowledge about the computer, because the computer already can be very harmful if you click on anything, and then you may have on your computer such type of viruses or other things which could be harmful for the whole society. So, therefore it was some idea, and they made also some exams like ACDL or whatever type of exams, but no obligatory things. So everybody can be like super user of any computer just because by computer, and I think the AI is just like a part of that, like computer application. So it would be also, and it's very dangerous again, like people may misuse it very easily, and but I can't see, because of the market, I can't see that there could be any point, because even they are harmful, these are not harmful as a car, which make an accident and anybody can see that, oh, it's physically happened here, something, and we should do something based on that. So
we are now about basically the other part of the sentence. The first sentence, it's about the social control of the technology, yes, which is closely related to a famous dilemma called Collingridge dilemma. I don't know if you can present it, but basically it's about a dilemma of we cannot regulate something which is at the first phase of development because it's not well developed enough to be interesting or be well able to well regulate. But after it's over our control, it's very hard to supervise it because, yeah, it's out of control forever. So,
Okay,
yeah.
for lawyers, it's a question of legislation.
Yes.
But when do you introduce a new act? Because if you use strict acts and hard acts, what should it do? Maybe it will be bad for spreading the technology, because the developers will say, oh, it's a barrier, I won't develop that project, I move to another project. And in the long term, the society loses many opportunities with this. But if we do not regulate some new technology, it can be the emerge of many threats and dangers, and for example crimes, if you don't prepare for them. And this dilemma leads us to the question when to regulate and how deep we have to regulate. And this is the same thing you could see in the EU AI Act. It was a slow process because they didn't know when to act and how to act. And they modified the proposition many times, if you can remember, because generative AI appeared and spread out. So this is the basic of the problem, I think.
I think one of the basic problems is here that the technology is changing so fast that nobody can really trace it. Like in every day they have new announcement, new versions of things, and even from scientific point of view, you cannot make any research on something which is always changing. Then nobody can reproduce anything because it's already totally different. So it's very hard to say anything from that point of view as well.
And regulate as well, sorry.
Yeah.
It's the same for regulation.
So some leaders, CEOs of companies who are doing this AI technology say that we will probably talk about the AGI question, whether it comes or not, but many say that yes, it's coming, but the humankind is not ready for this.
Not ready for that. Okay. Let's see some aspects of this potential danger or challenges, I would say, if I want to be positive. For example, the famous black box effect, which means that we cannot really explain what's happening and how it is happening inside the technology. Of course, it is a very hot topic also from scientific point of view, because explainable AI is a phrase, but I'm not sure to what extent we can really explain even a classification task, the most straightforward task AI is used for from people who are out of this circle. So why this decision was made by the AI or with the help of the AI?
Yeah, of course it is a really hard question. The explainable AI is something what we would like, but it's hard to achieve. But even if it is not exactly explainable, so because of the way they work, still there are some methods to analyze somehow the behavior. I mean, for example, yesterday Giuse told about such things. They tried to discover some behavior patterns of the LLMs. So it is possible, maybe not exactly, but it can be similar to how can we explain how the people think and work. It's also a hard question, but we have psychologists and other scientists who are thinking and working on this to explain or analyze how people work, and we can do something similar with the AI.
Yep. My mathematician brain says that if something is not proved or just more or less proved, then it is not proved.
Okay,
so it's a statement cannot be a statement until a justification.
But even in the mathematics, there are some For example, Riemann or Fermat.
Yes,
but
but
we think that they are.
Until
true,
it's just a conjecture, we think that it's true, but we don't use it to support other decisions or other theories.
That's true.
Yeah.
Okay. Oh, sorry.
Yeah, I just want to say a skeptic view that we started with the brain. Yeah, we had a nice talk about the brain. We don't understand how the human brain works, but that don't think that is justified. That we need to do something which are so complex that we don't understand. I mean, you can write some computer code that if you want to trace what is happening, because the computers know very fast. Nobody can really trace by hand to see that how it will be, because we just don't have enough time to do it by hand. And now we have even more complex systems, like billions of variables and so on. We can even have no chance to describe them. So I think that in science we want to understand how things are going, and we want to apply something based on our understanding. So therefore, here we have a hole in the system. We designed something which we don't understand, then how we can trust in it. So that's a crucial issue here.
Yes, I think that law exactly sees that problem. But according to the Coleridge dilemma, they said if we don't want to make the technology unspreadable, we have to live with this, because black box problem is against the basic principles of law. What are the basic principles? Transparency. This is the most basic concept behind the regulation of AI. And lawyers know that it cannot be fully transparent because of the black box problem. But still, they say, okay, it can go because the possible advantages for society are better. This is the paradigm today. Maybe tomorrow it will be another, but there has to happen something to prove it and to change this paradigm in the legal thinking, I think.
Back to this aspect. What do you think? Who is responsible for these decisions? I mean, especially who is to blame if the system makes a mistake? For example, a self-driving car. That's the typical problem. A self-driving car causes an accident, or there is a wrong decision in a classification task. Who is responsible? The algorithm, or who cannot be because it's not a person, or the programmer, or the company, or the user?
It's a question of product liability mostly.
Yes.
But it depends on the court of the European Union, the court of China, the court of the current nation states or states, because not an AI Act will say the answer for that. The national law. In Hungary, the Hungarian Code on Civil Law. So that's an answer. But basically,
I mean, that's the legal answer.
That's a legal answer.
But
okay.
what do you think personally? I mean,
I think the ethic answer is is close to the legal answer, because there is a thin line between were you just carelessly, or did you want this thing, or you didn't have the opportunity to do something. Because if you didn't have the opportunity with a self-driving car, because the producer told you that you can sleep and it will take you from point A to point B, then it's clearly, I think, both in legal and ethic ways, it's clearly the fault of the producer or the developer. But if there was a document and told you not to sleep in the car because it can drive itself, but just in a limited way, and you have to look around, then you also can be, because you didn't want the accident, but you didn't do anything to...
Yeah, that's an interesting issue because the companies wants to sell and therefore they have the advertisement. And maybe you have a contract which is like 200 pages, very small letters, and nobody can read. Like even if you want to use some softwares, the things that you need to scroll and you can click in there and yes, I read and I agree everything. It's more than a sound book. Like it's 10 hours if you want to read all. So that's nobody will read. And then we cannot say that. Then everybody is using this program without having the real license or without that, because the companies made it, and the companies made it in such a way that they expect nobody will read it. So, and if in the advertisement you see that, oh, you can sleep, so that's I feel very similar issue when many people in Hungary had some bankrupt things because they get money in Switzerland franc from the bank because the communication was not correct. So
I totally agree with you because you have to make clear instructions for the consumer. But most businesses didn't do it because what you told. But look, we have good examples. For example, GDPR, information, privacy notes, or information on data processing. They have to be clear for anyone. So maybe it would be a good solution if someone, law itself, would say that okay, but you have to read it in a short and understandable way. The rules, how to use it, a handbook. Sorry.
I think maybe very similar with the AI. If somebody wants to use, but the problem is here that if you write some web address which is, I don't know, located in which country, in which language, or for which law, you will get some things.
Interesting and good question, and we see that different countries have different opinions or decisions. Like the European Union has a little bit more conservative law or act about the artificial intelligence. The USA says that more freedom. They don't want to control the AI so much, and probably because of that they will win and we will lose. So there is maybe one not so bad such AGI direction AI in the European Union, and there are lots of such systems in the USA and in China. China is less conservative than the European Union. It's interesting.
Another example came in my mind because in the self-driving, the autonomous driving case, you are right that maybe somewhere in the 250th page there is a small footnote that please always keep your hands on the wheel, which makes it clear that it's your fault. But when you may remember this famous case when an AI chatbot pushed a teenager to kill himself, to commit a suicide, and the mother is suing the tech company because she thinks that without this AI chatbot, without the unsupervised response of his son's questions, it wouldn't happen. So what's your view in this case? Because in the website there is nothing like please don't use ChatGPT for psychological discussion or something.
Yeah, like
nothing like this.
Like in the USA, that you should not use the microwave to dry your cat. Yeah, maybe they should.
So there is no warning sign in the website that it could be dangerous.
Okay, but there were similar cases in the past and not even according to new technologies. For example, there were kids committed suicide because of classic pen and paper role-playing games, then PC games. So there were always something to blame for the death of the children. I would say it's very interesting, and I think legally the company is in a very hard case, because there is a big ethic pressure from the society that, okay, they are the ones who can blame for it. I think 80% or at least 70% of the people think this way. If there weren't AI, there weren't deaths. And of course we know the legal outcome of such cases, so it's not as clear as the society thinks. What basically I mean, and not the law as you said, I think it's unfortunate things, but not 100% the wrong came from the technology. I don't know. Maybe you have a better answer.
No, we don't have to create final answers for now.
But I think there is not a clear answer for that problem.
Okay. Okay, let's turn towards more positive aspects, the creative aspect of AI. Although there will be legal issues also in this case. Is AI creative?
Oh.
Yes, it is.
It is?
No, I mean...
No, it's not.
It depends on.
Depends on. So it's yes or no or maybe?
Maybe.
Okay, why do you think that it's creative?
We can check it, and we see that.
So it's obvious.
It's obvious, yeah. So it can create new, non-existing things, models, programs. It can write poem.
Why it's not creative?
I didn't call AI when I was like 12 years old, and randomly I put together some phrases and I was laughing on the result. So that's, I mean, these large language models learn the language, not knowledge, but the language. And in the language we can tell various sentences, some of them true, some of them false, some of them may be meaningless. So I don't think that it's just creativity just to have an arbitrary sentence. That's like, if you think about linguistics or generative grammars, which were used to when they developed the programming languages, then everybody know that, oh, it's a very small something and you can generate whatever you want. But if you don't know what is the meaning or what is the purpose, then it's hard to say that it's creative. I mean, it's more like ad hoc.
I would say it's connected with creativity, but maybe you're right, and it's more a tool of the creativity. Do you know here the Spring Breeze case from China? Li contra Liu.
We can, yeah, you can describe. I know it, but you
Okay. So it's it was the first case when the Beijing Court of China decided that a piece of art created by AI is an intellectual property. It was the first case. And what did they say? They said that it's just a tool that makes creation and creation of art more easier. Because let's think, the prehistorical man or the man of the antiques, they had to work hard on create art. They had to carve some symbols into stone, into wood, or I don't know. But after a few hundred years, there came the oil and canvas, and they became standard. And a few months ago, maybe you all remember, we saw an installation. It was a white wall and a yellow banana. Is it easy to create? Technically, yes, it is. But it wasn't my idea, so it's not my intellectual property. And the Chinese court said that if you have enough human input and you create with AI a piece of work with this, This is your intellectual property. But it's, in contrary, I have another case which I read about a long time ago, the monkey, the selfie of the monkey. It happened, in 2011. And what happened there? A photographer gave a camera to a monkey, and the monkey shot a selfie of itself. What happened? First, animal welfare organizations tried to prove that this photo is the property of the monkey. But a monkey cannot have intellectual property because animals cannot have, only humans, according to current law. But then there was a trying when the photographer started to say, no, that's my private intellectual property. Yeah. And what I want to ask you, if I may, what is the difference between prompting on a computer and prompting the monkey? Because if I give a camera to a monkey and show him that, okay, push that button, what did I do? I prompted the monkey. Is there a difference between this kind of prompting and the other kind of prompting? What do you think about that?
Personally, I am shocked that for centuries and still think that we don't give rights, that kind of rights to animals, to plants, no copyright for a tree or something. And now suddenly we want to give copyrights exactly. to a machine. That's really crazy in my view.
Yes, but maybe it is not necessary. Just for 1 minute to the previous question, when I said my opinion is that the AI can be creative, I think that if you see the results on the mathematics Olympiad problems and the programming competition level, and there was, for example, an experiment I don't know how many, but hundreds of people to read poems created by human and AI. And one of the results was that they could not tell which was the AI and which was the human. The second.
But maybe this sentence is about the evaluators and not about the poem.
Maybe, but that tells something.
Yes.
The second is that when they gave the rating, in average, the poems made by the AI were higher rated, and the third, that the human still has a bias. So when it was told which this is the human poem, this is the AI poem, then the people gave a higher rate to the human poems. These were the three results of this experiment.
That's interesting because my question would be that how much these people who evaluated speak with other people and how much they chat with AI, because that would give also a bias on the thing. Maybe they think what is nice or what is the real language is now what the AI generates because they met more with that.
But there was a similar experiment that human experts and AI gave explanation about Java programs, and the explanation of the AI were rated higher.
Actually, we jointly have an experiment of creating poems by the AI. And if I can say, we created, first I asked the AI to create Shakespearean sonnets. Because, why? Because there are lots of Shakespeare sonnets, like 154 or something, and it's quite strict in terms of formal appearance, and yeah, it created an average Shakespeare sonnet. If I can say there is an average Shakespeare sonnet. The question is, do we need yet another Shakespearean sonnet? Do we need the 155th sonnet? Is it okay to create another sonnet in Shakespeare style?
Yeah, good question. Maybe the rise of the AI will not be good for the humankind. I don't know, but it happens. So, and from a researcher, scientist viewpoint, I don't want to maybe such opinions. I just I'm just curious what happens, and I want to follow it. And really we don't know. And some big guys, I mean, for example, Elon Musk or Bill Gates. Some of them say that it's 50% that it will be good or not. Maybe Elon Musk gave 80% that it will be good for the humankind. But we don't know. There is a high risk because the prediction is that so some say that this year, some say that in 2027 the AI will be more intelligent than the human. And from this, when it happens, then it will change everything because the AI doesn't have to sleep, to go to holiday, so it will work continuously. And today there are millions of GPUs, maybe billions, I don't know, but at least millions of GPUs running such AI. And this number grows.
Yeah, actually there are millions of people who write poems, but there are only a few good poets, so quantity doesn't mean quality automatically.
Yeah, but the machine or the AI has one advantage against people, that the knowledge transfer is much easier.
Yeah, I have a provocative question for that, because considering the training of the AI, we need enormous amount of data. And I have a feeling that we already fed the beast. Whatever we have found, we pushed into the AI, especially in these generative AI, close to generative AI, large language models or such kind of things. How to create or how to get more data. If we have all the data now inside, we try to create synthetic data, which is completely crazy because it's just an endless circle.
Yes, this is really a very important question, but probably this is one of the reasons why these big companies give huge capacity with a large amount of money for free. They give it for free for the people to get responses, feedback. So the people, maybe hundreds of millions or maybe billions of people are using. And they give always, they give feedback. And the other one, what you said, that the synthetic data, it is said that nowadays the training contains more and more portion synthetic data.
Yeah, but synthetic data is something which is self-contradiction in my view. In this case, when you want to create a creative mind, and you create the data from data in a way that it cannot be really new.
But
mathematically cannot be really new.
No. I think that you underrate the AI. So try to compare it with the human. So the human also learns from the human, and not from someone else. The AI can learn from the AI because it's creative. So yeah, of course, if you set the temperature to 0, then it's not creative. It will give the same answer for the same question. But if you allow the creativity, then for each try it will give a different answer. So it's creative. And if the quality can be measured, yeah, sometimes yes, sometimes not, then for example in programming the quality can be measured because it praised the program, it tries to run it, and if it fails then it's bad, negative reward. If it's okay, then it's positive reward.
Okay, one last sentence, okay, because we have run out of time.
I just wanted to go back to this Shakespeare, because for Shakespeare I know the Legoland's fair. That's no problem because Shakespeare died hundreds of years ago. It's much more problematic if you want the style of an existing or living somebody. That's totally different question.
Actually, artists, there was a big survey among artists what they think about this stealing their work for feeding the beast, and they told that they don't mind if their artwork is fed to the system, but they don't want others to make money from that, which is a crucial point of view. One last question. In 10 years, do we need a programmer? Do we need a lawyer? Do we need a scientist, a researcher, a philosopher? Or AI will solve these particular problems?
The CEO of the...
Do we need you?
Probably not. The CEO of the CEO of the Anthropic company who created one of the best AIs, he said that maybe in the first days of April, so 2 months ago, that within 3 to 6 months the programming will be done, 90% of the programming will be done by the AI, and within about 1 year, all.
Okay, so we don't need programmers. Yeah, that's a fine question. Do we need lawyers?
I'm not sure. In 10 years, maybe we still will need, because just think of about the bias in the criminal law. Because we have to underline that AI in its current state can be sexist, racist, and many things. And you cannot use it. Okay, we can AI, and we actually use AI in public administration, for example. So there are relatively basic cases, and not all public administration cases are basic, but there are many basic cases, and AI will be good for that. So I think it will appear in the public administration first, and the last stage will be the judges, I think.
I see. Do we need philosophers and mathematicians?
I think we need somebody who takes care about the things if everything is going in some good money, or otherwise we lose everything, or we may lose everything. So I just send this.
Okay. Please study philosophy, not computer science.
Or not law.
Thank you very much for your attention. I'm just sorry. Yeah, sure. I don't know if we have time for questions.
So,
philosopher and mathematician thinks about the fact that we are betting that the consciousness is going to emerge from a matrix multiplication. So the current AI is reduced to matrix multiplication, and we are betting on AGI. So as a mathematician, how do you feel about this?
The interesting thing is that strong AI cannot exist on silicon hardware. So, I mean, the computer never get such type of understanding as a human. There's
not going to be AGI.
That's by the Gedanken experiment by Sears. We can see this. On the other hand, there are many efforts that the AI wants to show that it likes a human, it works like a human. And I just want to say that was in Google there were many projects, like to have the chess, the Go, and so on. They had also a project when they wanted to beat the human champion in some arguing competition. And the person who led that project had a very interesting, I mean, he was invited speaker during the pandemic in a conference and presented about that. And he told that they hired some of the previous champions to develop to help to develop their software. And it was a very crucial point when they understand that the logic of the argumentation arbitrary. It doesn't need to be mathematically correct because there is a human jury. You just want to convince the jury, and the jury doesn't have time to check all the details or whatever. And I think that's a crucial point, and from that the AI became very, very dangerous, because for politicians, for anybody, they can just use the AI to mimic something or to fool the people, because people want to believe. If you hear a sentence, you think that, oh, it's true, this is why this sentence came. And something which doesn't care about truthness at all. And now all the internet is like that. When the politician said that, it's not interesting if this is true or false. What is important, what will be the society reaction? So everything is going in a strange direction, and therefore I will not answer about this general AI thing, because somebody has always said something is clever, more clever than the human. What does it mean, the human? That's who? I can tell somebody who is that clever, somebody who is other. We are very, very many different type of people. So when we compare ourselves to, so I don't think that this would work in this way. So always we will need some clever people who can see what's going on and try to have some influence. But the problem is that if we have these large companies who has all the money and all the efforts to bring the world in one direction, then it's very hard to say that, stop, we don't need so much energy consumption for something which is totally useless. Because what people are doing, playing within the smartphone. You can't say that, don't play with the smartphone anymore. So, yeah, that's...
I totally disagree. Because,
this is why we are.
I think it's obvious that it's getting more intelligent than the human. Yeah, one of the questions is that it will be more intelligent than some human, or average human, or all of the humans. This is one of the questions. And the second is exactly when. Or AI, and the third question, or no, this is the second, and the previous was the third, because the intelligence is multidimensional. So it's also a good question in which kind of intelligence when. But it's obvious that it's getting more and more intelligent, and the human doesn't try to compete.
I don't know if he gave an answer for your question, but yeah, there is no final answer. Further questions?
I have quite a bit of points which I would like to raise. I'd like to see your opinions on these ideas. Also about art, it is in my opinion that AI is not creative, as some of you might agree, some of you might not, but it is very good at mimicking creativity. The reason why I believe this is, for example, if I take an art piece, I divide it into lines, and then I take a color palette online. First one I see, I don't choose, just one I see, and then I switch the colors of that painting with the ones I found. Am I an artist? I didn't put any emotions, I do this systematically. Maybe I even write an algorithm to do it automatically. That doesn't make me an artist, and this is in principle what AI is doing, but with a lot more parameters than just colors. It's also doing it with how round it is, and a lot of the time also there's a lot of examples online about a lot of art being stolen. Art that some artists made, being posted again as AI asked, and it's very similar to what they have done. But when an artist does something, there's a high chance that what they've done hasn't been done before, which isn't true for AI, which is also an example, and I think this also applies to the Shakespeare example, because art is one of the more pure forms of creativity. As for prompt engineers who tell the AI what to do, I'd like to ask a question. If the art teacher tells me to do something, to make art, and then I make that art, is that mine or is that the teacher's?
For the first question, if you don't mind, for the first question, if it's art, if you don't intend to make art, that's a philosophical question of what art is. So there are two ways of considering art. One way is to think that if you create something intentionally in an intelligent action for art, that it's art from your point of view. And the other view is that if the consumer considers it as an artistic piece, then independently of what you think about it, or what the nature think about it, it can be an artistic piece. So even this can be an art, even if our colleague didn't think that it's an artistic piece. But if you think that it's a beautiful piece because it's black and whitish, and that's a beautiful name here, that it can be an art for you. That's a philosophical question, and there is no decisive answer for that. For the question, if this piece of art, can I say, is yours or the teacher's, I'm not sure.
Isn't it a question of human rating? I mean art. If something is considered to be art by many people, maybe not all of them, but by I don't know, maybe 20%.
Actually, what I want to say is that what is interesting that discussing about AI, we have a lot of questions about notions which are with us, with the mankind, for hundreds or thousands of years, like what is art, what is consciousness, what is creativity. The only good thing, which is good for sure about AI, that we have to think again about these basic notions of the mankind. I think our time is way over. So thank you very much for coming, and thank you very much for the discussion. Thank you.